Hello, hello. Good afternoon. Good after. Good afternoon. Good after. Okay. Good afternoon, Vicky. Good afternoon, Aminata. Good afternoon, Gabriel. Good afternoon, Victoria. Good afternoon, Kian. Good afternoon, Mafine. No. Good afternoon, Vicky for the double. Good afternoon, Aminata for the double. Good afternoon, Roger for Roger. Good afternoon, Gabriel for the double. Good afternoon, Sonam. Good afternoon, Kaylin, for the double exclamation point and smiley face. The enthusiasm just woke me up. Thank you. Good afternoon, Mafine, for the double. Good afternoon, Victoria, for the double. Good afternoon, Kian, for the double. Hello, iPhone for the. I know who that is. Don't tell me. Wait, I know who the iPhone is. Not that it matters, but it totally does. Uh, wait. Okay, wait. I'm gonna. Don't tell me. And actually, and there's more people coming. All right, give me a pause for a second, or give me a. Yeah, hold on, and we will start in a second. I'm not trying to stall. Well, I'm never trying to stall. Hold on, hold on. Okay, I'm gonna go out on a limb. I have to do one quick thing here, but I'm going out on a limb, and I'm thinking. Oh wait, did you already? Oh, the iPhone. Oh, it was Fabia? Oh, was that? Oh, no, no, it wasn't. No, I believe the iPhone is Reina. Am I right? You wanted to, I mean, I'm not trying to call you out, but like, oh, it's Anthony. I'm sorry. Okay. Hello, Anthony. All right. All right. Good, good, good. All right. We're going to start in a second. Give me a second. And again, well, let me say, the exams are continuing to come back. They are not done yet. As you know, many of you have gotten yours. Many of you have not. They're just coming. Like slowly, but they're coming, and I apologize, and I'm aware. And let me also just say, I mean, dwell on it. There's nothing. They're just coming. You will get yours if you haven't yet, and it's not personal. Whether you've gotten yours or not yet. But you will get it if you haven't yet. And if it's freaking you out or upsetting you, like I understand that. I don't want to upset you, but like if you're starting to get edgy, just give me a like text me or email me and say I would like to just discuss my standing in the class for 15 minutes or something. And I'm happy to do that. Or, if I or I'm happy to do that. Like, because I get it and I apologize, but they are coming and they're just coming progressively through all the sections. So yes, so feel free to reach out and say I'd like to schedule a 15-minute talk or something like that, and that's fine. Sorry, wait. Oh, wait, there's a lot in the chat. Actually, give me and hello, Lear. Good to see you.
Hello, Professor. Good morning.
Oh, good morning. Good morning. Okay. Wait. Okay, there's actually a lot of people joining and a lot in the chat. Okay, give me a second. I might repeat the announcement I just made, or if maybe someone wants to. Oh, here would be a portal. Give me a second. I just have to fix something. Good afternoon, good afternoon, good afternoon, Lear. Good afternoon, private chat person. Good afternoon, Abid. Good afternoon, Joel. Good afternoon, Raina. Well, Joel, I know you've been here for a while. Anyway, if someone wants to put in the chat a quick summary of what I just said, that might be really helpful because I get so repetitive and rabbit hole-ish. And give me 1 second. I just have to fix something, and then but then we're going to start or go back to the material that we're at. But give me a second. But if someone, you could definitely submit for points. If someone could put in the chat essentially what I just said, that would, it might, I don't know, it would ease my conscience somewhat. But okay, give me 1 second. See you. I see you. Okay. Uh, okay. Oh, someone. Okay, no one wanted to do. I could see why you wouldn't want to put my words in there. All right, so I'm just going to quickly repeat now that I think everybody's here. And again, hello to anybody I didn't say hello. We're going to start again. Again, I apologize. The exams are just coming. They are. I certainly have not forgotten about them. I'm just they're moving very slow. Many of you have gotten one already. Some of you have not. It's not personal. They're coming. You will get them if you didn't get it yet, and then we can talk about them. But again, I just quickly say I recognize it makes it's not helpful to be waiting this long. I know that. So if you're nervous about anything or concerned or upset, just text me or I'll put it again in the thing or email me. I mean, even but there's no re you could just email me, but we could set up a quick phone call or something, even if I'm driving, um, so I can sort of reassure you of where you are in the class or what's going on. Just to remind you. Okay, that's just to say, I don't, anyway. But that said, there's not much more I can say about the exams right now until they all come back. So I'm going to go back to the material where we were yesterday. I mean, hello, good to see you, Melanie. Okay, so where we were was talking about flux, abstract concept. Frankly, one of my favorite. I love this topic for, I mean, whatever that is worth. Um, the result. Well, the law that I want to talk about today is this here on the board. I have a lot to say about it. Now, technically speaking, well, what this is a generalization, a universalization of a particular result that we concluded or found at the end of last class. It didn't look Well, it looked very similar to this, but let me remind you what we said from last class and from the first exercise in the homework that is currently on the docket and that I believe I can't remember when it's due. Is it due this Wednesday? You'll remind me in a second. But what we found. Ah, why does this happen? We found, so I'm reminding you, the specific example we're dealing with is that if you had a point source, a positive point of charge located somewhere in the lab or somewhere in space, like you have a proton sitting there, and then you imagine a sphere of radius r surrounding this point charge, right? Well, yeah. If you imagine the space, or you consider the space surrounding the point charge, and you consider a sphere of radius r surrounding the point source, we asked, well, first of all, we asked to consider what the field lines look like. The field lines from a point source, the field line diagram from a point source always looks like this. And here, like my scaling factor, so to speak, is I'm doing 8 lines for every 1 Q of charge, right? Like I could have drawn 16 or I could have drawn, but I'm drawing 8 enough to see the pattern. The pattern of field lines from a point source, from a positive point source, is that they radiate out equally in all directions, right? That's the field line picture from a point source. We then asked, what is the flux? What is the electrostatic flux through the surface area of the sphere of space surrounding this point source, the sphere centered on this point source? We asked, and right, we asked, what is the flux? And I want to be clear about one thing before I go on. Like net flux, when I say net or something, what I'm getting at that things can flux out of an area or they can flux in. Whenever lines flux out of a surface, we call them positive. And if they flux into a closed surface like this one, we call them negative. So we were trying to figure out the flux through this concentric, excuse me, through this sphere, through the surface area of the sphere. And remember, I'm not going to redo the whole thing, but I am going to repeat the result. I'm just reminding you that flux itself is defined to be the total amount of field passing through an area perpendicular to that area, right? Like the definition of flux through any area is the total amount of field uh, flowing through that area, right? So the idea of flux was that if you take any kind of area at all and you think of yourself as navigating through that area or walking through that area, like take tile by tile by tile. You take a step on a tile, that's like a DS, an infinitesimal surface element. S stands for surface, right? So you step on a tile, you ask what's the field strength at this tile, i.e., how many field lines are passing through each square centimeter of this tile, right? Because remember, in a field line representation, it's the density of field lines that indicates field strength, right? It's no longer length of arrows, it's density of field lines that indicates field strength, right? So you step on a tile and you ask at that tile, what is the field strength passing through this tile, i.e., how many field lines are passing through perpendicularly through this tile. You take that total, the number of field lines, i.e., the newtons per coulomb, you multiply by the size of the tile, square centimeter or whatever, and you put that in your bag. Then you walk to the next tile and you ask the same question again. What's the field strength here in newtons per coulomb? Multiplied by the area, centimeter squared or meter squared or whatever. You multiply it together, put it in your bag, and you walk to the next tile. And you go until you've traversed the whole area, and that entire continuous sum of field times area is what we mean by flux, right? Now again, it's an integral. Integral always means continuous sum of products. Again, don't be intimidated by I mean, please try not to be intimidated by the fact that this is a double integral. It's double only in the sense that it's two-dimensional, that each element that we're integrating is an element of area. It's really secretly like a dx times a dy. So we're secretly really doing an integral times another integral. That's what, okay, it's a two-dimensional rather. So instead of walking on a path, we're walking on a path and then hooking a right turn and walking down a perpendicular path and getting the result of the whole thing. That's what we would do if we were mathematicians. But as physicists, we're sort of doing it all at once. We're stepping on square centimeters rather than centimeters. Okay, anyway, so I'm saying it's just an integral of dot products of field strength with area elements. That's what flux is always. So now we tried to compute it for this particular area that we had, which was the surface area of a globe, of a spatial globe, of a globe in our minds, of empty space globe, centered at a point source. And what we said, I mean, so this is where I'm not going to redo the whole calculation, although you really do want to know this calculation. It's often on the final. You want to know what we applied the definition of flux. We plugged in the Coulomb's expression for the field due to a point source, and by the time we were done, we got an answer that's that simple. That's a cue. That's where we left off um last Wednesday. Oh, I'm just switching the view on the screen. Oh, hello. I'm sorry. Okay. Now this is a big now it's a very specific example, but it's a very simple result. It's a very simple result that in some a very nice, elegant, like simple is good. It's a nice, simple result that in some ways may be the consequence of such a contrived example. But let's talk about that. Like, okay, okay. What this is saying, and I know I said this last Wednesday, but let me reemphasize this if you don't mind. I'm saying we want to know the total flux through the surface area of this sphere. That really means we're asking like how much field strength, if we added up all the field strength throughout this whole region, like what number do we get? And it seems to be the case is that it doesn't matter whether the sphere is really big or the sphere is really small, as long as it's a sphere and as long as it's centered on that point source Q. Apparently, the flux is the same either way. It only is affected by the strength or the magnitude of that charge Q. Now, what? Now we saw in the math why this happens. In other words, mathematically, the R of the sphere size cancels out of the result, and we saw that happen in the math. Mathematically, the r cancels out because the 4 pi r squareds canceled out. Because as you get to bigger and bigger spheres, the area, the surface area of a sphere is 4 pi times the square of the radius of that sphere. So as you're getting to look at bigger and bigger spheres, you're looking at a bigger area. So if all other things were equal, you'd be getting more flux. I mean, you're getting field through a bigger and bigger area. Flux is field times area. So as you look at bigger and bigger areas, I would think that we would be getting more flux if all other things are equal. But all other things are not equal. The field strength is getting weaker as we get to bigger and bigger spheres. And it turns out that the field strength is getting weaker at exactly the same rate with regard to space as the surface area is growing. In other words, the surface area of a sphere is 4 pi r squared, and the Coulomb's law for the magnitude of a field due to a point source is 1 over 4 pi epsilon naught q over r squared. It's an inverse r squared law being compared against a direct r squared law of surface area. So, in other words, the sphere grows at the same rate. The sphere spreads out at the same rate as the field from the point source weakens. So they cancel out, and the total effect of flux on a sphere is the same, is one number, no matter how big the sphere is. It only depends on the charge inside the sphere. Now, there's a lot more to say, but let me pause on that for a second. Well, the key point here is that the surface area of a sphere, 4 pi r squared, grows at the same rate as the field from a point weakens. Like that's why the math worked, right? But but take a moment to appreciate that, please, or to try, because that's not a coincidence. It's not a coincidence that spheres grow at the same rate that fields weaken. Oh, I'm saying, I'm saying gravity is gmm over r squared. Electrostatics is kqqq over r squared. The two forces that we know that act through empty space that seem to embody action at a distance, the two forces we know that just kick into activity just as long as objects are sitting around existing, like whether they're points of mass sitting around and existing or points of charge sitting around and existing, the forces that things exert just that the forces that objects that thingy things particles exert fundamentally are inverse r squared forces, which at first looks really strange. Like, why would gravity, like why would gravity like have an r squared in the denominator? Like maybe you understand why the like the weak the far well anyway, why would gravity have an r squared in the denominator? It's so obscure and inconvenient looking at first. And then why would electricity also have an r squared in its denominator? Why would the two forces that just act automatically through empty space both be inverse r squared forces? It can't be well, maybe it could be a coincidence, but it seems like it might not be. Well, what we're saying here is once we start thinking about flux, it starts to really become clearer and clearer why these forces look like that mathematically, because they're just spreading out through space equally in all directions. Remember, I said, like last week, like field lines are an expression of asymmetry. Field lines are only as asymmetric as the things that cause them, right? That if there were no objects in space, there would be no fields in space. There would just be space. Space itself is purely symmetrical. Once you put things in space, then you're creating asymmetries in space. What I'm saying here now is you put a dot in space, you put a proton in, it creates an impact on space. It spreads out the information of its size and its location throughout space, but it spreads it out equally in all directions because all directions of space are indistinguishable from one another. Space itself is symmetric. So you put a dot, like a proton, in space, and it tells the world, and it starts pushing on the world, saying, if there's any other proton anywhere else in the world, I'm going to push on it, right? Or you put a dot of mass in space and it's going to start pulling on the world, whatever, right? But it's pulling on the world equally in all directions. Its influence is spherical, right? And its influence gets weaker and weaker in the same way in all directions, weaker and weaker in the same way that a sphere gets bigger and bigger. So basically, what we're saying is, right? So this is so flux, for starters, helps us start to realize what the inverse r squared is all about, and why, by the way, why we write that constant instead of just writing it as k, we write it as 1 over 4 pi, so we can see these 4 pi's clearly cancel, and we can really, picture the concept here. The concept is that the effect of field spreads out and weakens just in the manner of a sphere, like rippling out in all directions, like three-dimensionally from a point. I hope that makes some sense. So the total impact of a proton, the total impact is the same whether you add up all of its strong pull pushes right here, or you add up all of its weak pushes all around here. It's the same proton, it's yanking or shoving on the world in the same way. The total impact of the field here is the same as the total impact of the field here. That impact is called flux. Good. Something's in the chat. Thank God. So it's yes, yes. So someone in the chat wrote, so would smaller radii always indicate greater force? Yes, always, as long as we're talking about the fundamental force of electrostatics. If we're talking about electrostatics or the fundamental force of gravity, yes, yes, that's what the r squared in the denominator of the force really means. It's weaker and weaker. In other words, okay, so yes, very good question. And I got one last way to put this. I'm saying to everybody, what you might not be surprised to know, what you might have guessed yourself before we started all of this, is that gravity would get weaker as you get farther and farther away from a mass, or that electricity would get weaker and weaker as you get farther and farther away from a proton, right? So if it were up to you, you might have, or I might have come up with the idea that r, the distance, had better be in the denominator. Like it better be an inverse proportionality between the strength of the field and the displacement from the source of the field. To me, what the mystery has been up until now is like, okay, fine, R is in the denominator of Coulomb's law and of Newton's gravitational law. Fine, R is in the denominator. But why is R squared? And what I'm really saying here, folks, is R is squared because we live in three-dimensional space. Like I'm saying it's squared because the weakness, the the rate at which things get weaker, forces, influences get, it's like it's where the expression sphere of influence sort of comes from, or you could picture. I'm saying the influence of a proton on its surrounding neighborhood drops off as a function of r squared, not just r, because it's spreading out in all directions. So at any given moment, you want to see what its influence is. You can picture the surface area of a sphere, and the surface area of a sphere weakens as a function of, or I mean, grows as a function of r squared. I like I I might be able to explain that a different way in a few minutes or something, but that is what I'm saying. And if you are following me, then then it'll occur to you, or you'll follow the next thing I say. Like this does mean if we lived in a two-dimensional space, if our world were flatland, I'm not saying it is, but like it, if we lived in flatland, then the gravity law would be GMM over R, and the electrostatic law would be KQQ over R, not R squared. Because it's one dimension down. But okay, I'll leave it at that so I'm saying this is not a coincidence. I'm saying no matter how big the sphere is, the flux is going to be the same. But then, so what I am saying is that field in general weakens in field from a point spreads out like a sphere. Field lines spread out like radii of a sphere. And they get weaker and weaker, i.e., they get less and less dense, right? They get farther and farther away as you get farther and farther away, um, at a rate of 1 over r squared. So I am saying, no matter what sphere size you try to capture these rays, like no matter what sphere size you try to capture these field lines, you're going to get the same flux no matter what size sphere you choose. Um, and I mean, slight sidebar here. If you're having, remember, flux is field times area. I keep saying we're living in a three-dimensional space, and I keep talking about globes and spheres, but then I do a flux calculation for the surface area of the sphere. That's not a mistake nor a coincidence, but it might be confusing to some of you. Like I seem to be going back and forth in my discussion between three dimensions and two. I am. The one way to see that, like there's a reason for that. It's kind of like if light is everywhere in a room, if you have a flashlight and you turn on a flashlight and the light spreads out in all directions of the space of a three-dimensional room, if you want to see the effects of light, one of the most direct ways to observe or measure the effects of light from like a flashlight or or whatever in a room is with a screen, right? Like you would put up a screen somewhere, you would take a slice of the three-dimensional room and light would hit that screen. And by seeing how light hit that screen and where there was light or where there was shadow on the screen, you would get a very good, if not very precise, sense of what the light was doing, right? We use screens which to observe and measure light. Light spreads through three dimensions of a space, but we catch it or we grab it or we measure it or we isolate it or we focus on it. No pun sort of intended. Um, by looking at cross sections of three-dimensional spaces called screens, or in other words, called areas, right? So we observe light's three-dimensional behavior on a two-dimensional slice. That's kind of like what we're doing with flux. With flux, we say there's field lines going everywhere in three-dimensional space, but if we want to measure them or see their effect, let's take a slice of space, an area. Sometimes the area is open, sometimes it's closed, but we count up the number of field lines through that area and we call that total effect of the field lines throughout the whole area, we call that flux. And it's kind of like measuring the impact of light on a screen. So I don't know if that helps anybody or not, but my question now is, okay, but does this whole flux calculation that we did last week, like it seemed to have been very simplified because we only looked at the flux through the surface area of a sphere. Like what would have happened if we tried some other shape or something like that? A good question. The answer is no. We could have tried some other shape here. Once we see, okay, we just argued what the flux is through a sphere, and we just found out that the sphere could be of any size and the flux will still be the same. It'll just be the amount of charge over the constant. So now I'm saying, well, wait, that's actually pretty powerful because so if you're picturing a sphere, right? Let's start picturing like other shapes besides a sphere. Let's imagine for a minute that the sphere is made of clay or something, and you start distorting the sphere by poking the clay, like maybe taking a little piece of the clay out over here and pulling it out a bit. So now it's like a deformed sphere, right? And maybe taking some clay over there and pushing it in, or maybe you make like a really deformed, weird sphere with like clay at different places, or maybe you just keep doing that until you straighten out all the clay and you have like a cube or something. The thing is, so now you have a totally different shape, right? And it seems like the argument we just made was about the shape of a sphere. But the thing is, if you moved all that clay around, all you did was take each piece of clay and change it to a different R from its neighbor piece of clay. Like what makes a sphere special is that all the points of a sphere are all at the same R. If you change from a sphere to some other shape, you're changing the R's for sure. But we just concluded that R doesn't matter. We just concluded that the flux would be the same whether the R is really big or the R is really small. So if you vary the R throughout your sphere and end up with something that's not a sphere, so what? You're still like, we just said R doesn't matter. We just said that the flux is independent of R. So even if you vary R, you aren't varying the flux. So apparently, in other words, apparently, I'm still number two here. Evidently, then, um, so what I'm arguing so far, okay, we're analyzing like one particular example, an example of a sphere centered on a point source. And we've so far said that the total flux through the sphere centered at the point source. So far, we're saying the total flux does not depend on the size of the sphere. Now I'm arguing by sort of a weird argument. I'm saying, well, if we really believe that, if we really believe that the total flux um, uh, uh, through the surface area doesn't depend on the size of the sphere, then if we take that really seriously, it doesn't even depend on the shape. Like it doesn't even need to be a sphere, in fact. As long as it's some sort of closed shape, um, apparently the flux is still going to be Q over epsilon naught. And I'm going to go a step further. Then I'm going to go a step further and say, well, wait a second. If Very good. Yes. I was about to say the name. Sorry. Direct chat person. Yes. So a direct chat person just said, so this is like saying like the amount of clay, the amount of clay. Right. So it's like saying the amount of clay doesn't change regardless of shape. That's very good that you're staying with my clay analogy. So yes, and let me modify that slightly or go even further. Like what I'm really saying is the number of field lines that hit the clay won't change no matter what you do to that clay. And yet, which is effectively what you're saying. Like, yes, even if I play with the clay, as long as I have a certain amount of clay, right, it doesn't matter. Well, actually, I am slightly modifying what you're saying. Like, I'm playing with this clay. First, it was a perfect sphere surrounding this point, and the point is bursting out field lines to the clay. Then I start playing with the clay. Maybe make it bigger, make it smaller, make part of it bigger and the other part of it smaller. And no matter what, the number of field lines from the point that pass through the clay will be the same no matter what. So I mean, I love what you're saying. My slight modification is you could even change the amount of clay. I'm not even saying that the amount of clay can't change, but I'm saying as long as the clay surrounds that point source, the number of lines that come out of the point source through the clay and like hit the clay, that number of lines won't change. If that makes, oh good, good. All right, cool. And I'm going to go further with that to everybody in a second. So now I'm going a step even further, and I'm saying, well, if that's true, if it doesn't even have to be a sphere anymore, like it could be a cube or whatever, well, then it doesn't have to be. Then each field line it doesn't have to be equal. Like all the radii don't have to be equal anymore. Then there's nothing, symmetry is not required anymore. So there's no reason that the point has to be at the center of this whole thing. In fact, if it's like a cube or a rectangle, I don't even know what a center, maybe it's some shape that I don't even know what the center is. The point doesn't have to be at the center for this to be true, is what I just said at number three. Therefore, and I'm going to believe me, I'm going to give you a different way to look at this in a second. Like I'm totally psyched that the direct chat person is like staying with analogies. I'm going to give you a different analogy in a moment, all of you, that will simplify this vastly, but I want to just give you all the facts before I do. So number four, Okay, what I'm saying here, number four. Okay, what I'm saying here, number four, and this is about to become like very important. I'm saying now, if the point source that's creating these field lines that are being measured or captured or intersected or whatever by some container, some closed surface, like what we're right, it started with a dot being surrounded by a sphere, and we're asking what how many field lines were going through the surface area of that sphere. But then we said the sphere, we got the result. The flux is the amount of charge, like the number of coulombs divided by a, a universal constant. We got this really simple result that said the flux through a sphere is just determined by how much charge is surrounded by that sphere. So if it's like one proton, then we get a certain number of newtons per coulomb times meters per squared for this globe. But if we went to a bigger globe, we get the same number of newtons per coulomb times meter squared from that one proton, right? That's our first conclusion is it doesn't matter how big the sphere is. Then we're saying, well, if it doesn't matter how big the sphere is, if you really think about it, and this can be proven rigorously with cosine components and everything, if you really think about it, then it doesn't even need to be a sphere. It could be any shape. So we're first saying the flux doesn't depend on the size of the enclosure of the surrounding closed surface. Then we're saying it doesn't even matter. It doesn't even depend on the shape of that surface. Now, then we're saying, well, it doesn't matter where the charge is located inside the closed surface. As long as there is charge there, it's going to create a certain amount of flux, and that flux will be that flux regardless of where the charge is. And if that's true, that means for every one proton you could ever picture, for every one dot, the total amount of flux coming through a shape surrounding that dot will be an amount, Q over epsilon naught. For each and every 1 point of charge, the total flux through any closed surface surrounding that charge will be a fixed constant amount. So therefore, if you had a whole bunch of charge, if you had a proton here and a proton here and a proton here and a proton here, and you surrounded them all, the total flux would be the flux from that guy, plus the flux from that guy, plus the flux from that guy, plus the flux from that. Like it doesn't matter, in other words, where they're distributed or how many are distributed or how they're configured together. I'm arguing, I'm arguing this. I'm arguing for any closed any closed surface in the universe, I'm saying, so if you have any closed surface, closed, right, i.e. container, like not an open surface, not a piece of paper, but a closed surface, like I think we discussed this last week, a piece like where you take the piece of paper and you touch all of its edges together you um so that you have a container, right? Just like, and then I'm pausing for a second. So remember, I'm saying flux itself is total stuff through area of any kind, right? The integral that defines flux is just a double integral sign. There's no circle on it. But now I'm saying, and so flux through open areas, so flux can be computed through open areas or closed areas, through open surfaces or closed surfaces. But what we seem to be concluding now is that as long as the surface that we're talking about is closed, as long as it constitutes a container, just like, right, with, remember, we said last week, with one dimensional regions of space, like you can have a line segment that's an open line, an open path, Or you could close it up and my fingers could touch together and then make a ring, and that would be a closed line. They're still both one-dimensional regions of space, but this is an open one-dimensional region of space, and this is a closed one-dimensional region of space, right? Same thing can be thought the same way we can think about areas, two-dimensional regions of space. And what we seem to be concluding now is that the flux, the total amount of flux through any closed area, through any closed two-dimensional region of space, will always be fully determined by the total amount of charge enclosed by that area. E and C means enclosed, um, over that constant. I'm saying. So this is a law, I'm saying. It's called Gauss's law. I'm saying, I'm going to write it again on the next page, but that's the law. Like, so the left side is flux, but flux through a closed area, a closed surface, meaning a container. And the right side is just charge, but charge enclosed, meaning the total magnitude of charge enclosed by what? By the closed area on the left-hand side of this equation, right? It's so we're saying this. I'll write it again. Very important law. I mean, really important law. Okay, I'm going to read this. I'm going to say a couple more things. Okay, it's 110. First, I'm going to read this. So what I'm saying, so this is a huge law. I mean, it sounds so abstract. It might sound so abstract, or it might sound so abstract, but and it is abstract, but it's I mean, it's a very fundamental law, and I also love it, but whatever. Um, what I'm saying about it at the moment is the English written here on the board. It says the net electrostatic flux out of any closed surface, like anywhere, like you just pick anywhere in space. You pick a container, like it could be, like the rind of an orange, it could be a tennis ball can, it could be a cube, like any kind of container you can imagine, any surface that is fully closed up. So sidebar, well, okay, I'll say the sidebar in a second. But so picture any container in the universe. Then what we're saying is, if you want to know the total flux coming out of that container, i.e., the total number of field lines coming, like if you wanted to add up all the field lines busting out of all of the walls of that container, the total amount of flux that you would get, the total number of field lines that you would, electrostatic field lines that you would get, would be fully determined, would be fully equal to, or fully directly proportional to the total amount of net charge that you find within the container. Like so you add up all the coulombs of charge that you find within the volume enclosed by your container. You add up all of the protons. It doesn't matter where they are. It doesn't matter how you're configured. You add up all of the protons, all of the net charge, and then you divide by the constant epsilon naught, and that will fully give you the number of field lines coming out of the container no matter what. I'm going to break it down further in a second, but just notice indeed so Q stands for Q enclosed. Enclosed by what? The closed surface that is being referred to on the left side of the equation. So we're saying the total amount of flux through any surface area bounding a volume is fully determined by the amount of charge distributed throughout that volume. That's what we're saying. Looking at the chat. Okay, let me break that down a little to be as clear as I can. Okay, what we're specifically saying, what this result is saying, and and I mean, you can very rigorously and carefully, sort of mathematically prove what I'm saying, but we just made sort of an argument, I think a persuasive argument by generalizing our simplest, most symmetric case. We started by surrounding a point with a sphere centered on that point. And then we sort of have been extrapolating, like complexifying that sphere, and at every step saying, well, this complexity that we just made, or this modification of the sphere, or this factor that we just unsimplified doesn't really actually seem to change our result if we really believe if our result really makes the sense that we think it makes. And so we've concluded that if you picture any surface, any closed surface, any container in the world, that the number of field lines coming out of that container will be independent of the size of the container, the shape of the container, the configuration, or in other words, shape of the charges within the container. And I might add, even though I didn't say this before, number 4 here on the list, it's independent of any charges outside the container. Like if you want to know the net number of field lines coming out of a container, all you got to do is look inside and see how many charges are inside. It doesn't even matter where they are, just as long as you know how many there are, and you'll know the total number of field lines coming out of the container. The reason you don't even have to look at any charges anywhere else but the container is that any charge everywhere else in the universe certainly will make field lines, but any field line that any charge anywhere else makes will make a field line that if it enters the container at all, will necessarily exit the container because the container is a container. It's a closed surface. So any charges over here that you might think, oh, wait, aren't they making field lines that affect the container? Yes, but in both directions. Like they're coming in and then they're going out necessarily, like definitely. So the net flux out of a container, out of a closed surface, is fully determined by the net charge enclosed within that surface. One Okay, and if you're saying anything like, well, I get that it's true, but I don't get why we care. Fair enough. I'm with you. I'm not hang on, like I will show you why. Well, but actually, I will tell you why you care, sort of, because, and I sort of promised this last week. I mean, I can't like give you the whole package yet until but the large reason we care is because in physics, we always care when we stumble on or discover something that remains the same, even when a bunch of other things seem to change. That's what we're always looking for in physics is constants, especially hidden constants, right? I mean, please never forget, like, I don't, I won't rabbit hole. um, but if physics is about prediction, the whole thing is to find. I mean, it's not interesting to make predictions when nothing changes at all. I mean, anybody can do that. It is interesting to make predictions when things seem to be changing. The only way to make predictions when things seem to be changing is to find something underneath the seeming change that itself is not changing, i.e., patterns, right? Like, okay, I will wrap it up, right? I mean, if they serve tomato soup every single day in the cafeteria and you walk in, you're like, I have a prediction. Everybody gather around. I'm going to charge money. I bet you tomorrow they're going to serve tomato rice soup in the cafeteria. Like no one cares because they serve tomato rice every day. I mean, for example, right? But if they change the soup every day, but you figured out that even though they change it every day, there's some underlying like rule, like it's always tomato rice on the third Tuesday of the month or whatever, then you can make a prediction that's like actually doable, but interesting. That's what we're doing in physics all the time. So the first thing I'm trying to say is this flux thing seems important because it's making us realize that field lines are constant under like a wider array of circumstances than we might have guessed. Okay, that's like the big picture of why we care about this. But but let me be more specific again. Okay, so first thing I'm saying, just notice we're getting into kind of like geometry concepts here because we're talking about how information is distributed throughout space. So we are talking about space. So just notice there's a certain like background assumption that I'm making in the way that we're talking about things here. and the background assumption is start with one dimension and two. Like there's this concept of open and closed. Equally, there's a concept of bounded or unbounded. A boundary is where a space changes, a limit on a space, right? So when you take a one-dimensional region of space, like a line segment, and you close it up and you make a ring, it does, or an oval or something, but if you make a closed path, um, that closed path is the boundary of the open area within that path, right? Like a circle is the boundary of a disk. If you could walk around the disk and walk around the disk, but eventually, if you go too far, you fall off if you're like a mosquito, you fall off the disk once you cross the circumference, the circle bounding that disk. So a disk, for example, right, or same thing with a square and the perimeter of the square, like or a rectangle. I mean, it doesn't have to be symmetric, but a disk is what is an open, bounded area. It's open because it's not closed, but it's bounded in that if you go sufficiently far in a particular direction, you're eventually no longer in that area, in that region anymore, right? So a disk is an open, bounded region of space. What is the boundary to it? A closed one-dimensional region of space, which we call a circumference or a perimeter or something, right? I'm saying a closed one-dimensional region of space is the boundary. It bounds an open two-dimensional region of space. Like you sort of always knew that, but didn't necessarily care, or it turns out it matters. And similarly, a closed two-dimensional region of space is the boundary, or it bounds a three-dimensional region of space, i.e., a volume, right? We're sort of just so only in the case of a volume now, what I want to say is a because we live in three dimensions, I can't, I mean, there might be a fourth dimension, but I can't like picture it or measure it yet. So so I don't know what it would be like to warp a three-dimensional object like into the fourth dimension, but I know that when I warp a two-dimensional object into three and I close it up, I now make the skin of a volume, and it's a unique volume. It is one and only one. Like in other words, once you have a tennis ball can, it is unambiguous the difference between the space within the tennis ball can versus the space outside it. In other words, this law, Gauss's law, on the left-hand side is a closed integral. And by the way, familiar, just like at the beginning of the semester when we said like a conservative force is a force for which the closed path integral always equals zero. Like remember, a closed integral means an integral throughout a space that is closed, that where you could go far enough and eventually end up where you started, right? So we're assuming here that that a closed surface bounds a unique volume, an unambiguous interior that will allow us to then say, if you just count up all the charges that are in the interior, you're automatically going to know all the number of field lines that bust out of the container, the boundary of that interior. A closed two-dimensional region of space bounds a unique three-dimensional region of space. That's what we're saying. Now, and so Gauss's law is saying, in other words, what's going on the boundary is fully determined by what's going on the inside. The number of field lines that bust out of a boundary in three-dimensional space is fully determined by the number of charge points that cause them on the inside. Now, we have 6 minutes left. I want to go back to the person who was like sort of asking me, like probing the clay analogy, which I really appreciate that that person was doing that. Let me sort of continue with an analogy in a way. Okay. So remember, so I'm now going to try, we have 5 minutes. I'm going to try to put this in perspective, like another perspective on this law, try to make it more physical in a way. Okay, remember, flux is field times area. That's abstract, right? We're getting and now what I'm asking you to apply first, you have to picture field lines. Now I'm asking you to picture field lines through areas, and now I'm asking you to picture those field lines going through areas that are closed. Like it's like a lot in a way, right? But remember, flux is field strength times area. Okay, so flux is field strength times area. We have 4 minutes, but when you're using a field line representation, as we said that when you're talking about field lines, field strength is represented by number of lines per area, right? So if you're looking at a picture of field lines going through an area, what flux is, when we're talking about flux is field number of field lines per area times area, right? And this is actually really why Faraday started caring about flux. Like, right, with a field line picture, the greater number of lines you have per like square centimeter on the page is stronger field. And we're saying flux is supposed to be strength of field times area. So flux just means, hence, to measure flux is simply to count lines, literally. It's like so much simpler than all of this makes it sound. What we're literally saying is, and this is the last thing I'm going to write. I know there's like 2 minutes, 2 minutes. Hence, Gauss's law is saying the number of lines coming out of a container, emerging from a container, is fully determined by the number of charge points in the container. That's it. In a way, it's so. I'm back to the person with the clay. I'm literally saying, and I know we have 1 minute left. I'm saying, take any container in the world. If you want to know how many field lines are coming out of it, all you need to know is how many dots of charge there are in it. And remember, there was a scaling factor when you drew your field lines. Like you say, like for every 1 coulomb of charge, I'm going to draw 8 lines or something. So, duh, in a way, we're just saying if you've got 2 dots of charge in the container, there's going to be 16 lines coming out of the container, no matter how big or shaped the container is or anything that's going on inside the container. We're just saying what we're saying is with 1 minute left. And if you can get this, we're just saying it's just like water. We're saying if you had a spigot of water and it was spraying water out in all directions, and you put a tarp around to fully enclose the water, the total amount of water you'd catch on the inside of the tarp would be one amount of water, regardless of the shape of the tarp, the size of the tarp, or any other water, or how the water was distributed inside. As long as water's coming out of a spigot, for every drop of water that comes out of the spigot, a drop of water has to hit the tarp. End of discussion. So it's that easy. Gauss's law is, and I know it's 1:30. Gauss's law is that simple. We're saying the number of field lines through a container is fully determined by the number of charges causing those field lines. We're saying field lines act just like water. That's all we're saying. But that's a big thing to say because what we're saying in the end is information, raw, unthingy information in space acts just like stuff in space. It's never created nor destroyed spontaneously. You can only get field lines from charge points. So the number of field lines coming out of a container is fully determined by the number of charge points in the container. Field lines act like stuff. They're conserved. That's what we're saying. I'll see you Wednesday. You've been very patient. More exams will come back. I appreciate your everything.
Thank you, Professor.
Thank you. Thank you. Have a nice day. Yes. Have a good one. Yes. All good. Wait, I'm gonna stop there. Going once, Biana, going once, going twice. Have a lovely afternoon.